Okay. Good afternoon, everybody. So we're going to, uh, so before the second exam, we're going to spend 7 lectures on chapter 5 and 6. And then we'll spend 2 lectures on review. So 1 lecture just review doing homework examples on chapter 5, and another one review and problem solving skills on chapter 6. And then you guys going to have this second middle term on, I believe it's March 24, maybe right, that Thursday, before the spring break. So the last class during before spring break is the second exam. And then after that, we're going to go to chapter 7. We spend about 8 lectures on the actual content, and then 1 more lecture on the problem solving skill towards the end, and then you guys have the final exam on, I believe it's on May 8th. It's a different time, different room, but it's yet to be announced. Now, I just want to announce you guys here, last exam, overall class pretty well, but apparently some of the students, I was disappointed, but we didn't sit down. You guys to have access to your notes and your textbook. So make sure you download the lockdown browser and try. There's a test you can try before. You guys probably have done this in other classes, so you're probably familiar. But if you not, download that browser and open that browser and try it out. There's what you can print as many pages as you want. Bring it to the class. No electronics devices is going to be permitted during the exam. You guys are going to have to leave your phones on the side, laptop, iPad, tablet, everything on the side. You only have one access to your laptop, and you have a bunch of material from second the final exam. Our class is huge. ITs are not able to watch everybody with a close eye. Especially in here, your lesson is fair to everybody. So hopefully, as I said in the beginning, I want to help everybody. I want to help all students. I want you guys pay the time and tuition. I want you to be successful, but I don't want you guys to cheat out. Yeah. And I feel bad if you got a perfect score, and then I want to ask you what is the property of op-amp, and I couldn't answer. That's really not what I wanted to expect. Okay, so we're gonna go. Any questions before that? Okay, and also one more note: it's the next exam. Nobody's gonna sit in the last row. The very last row, nobody's gonna sit. Everybody sit to the front part. Okay. Yeah, it's working actually. Yeah, I think what happened was I log into a different people's account. Somebody didn't log out. I thought it was mine, okay. But then I figured out, so I log out. Okay. So it's working. It's working. Yeah, thank you. Thank you. Yeah. Okay. So when you write your notes, whatever you want to print out. I have no time bring with you. That's how you can print. Don't mind. People to cheat on by looking at ChatGPT. It's not that we do this class. I want you guys, make 100% out of the class, but not knowing anything. Yeah, you will get the degree, but it really doesn't make sense to me. Okay, I want you guys to know, learn the basics. I mean, that is why the problem is not difficult. You know the basics, you know the concept, you can do well. I don't want to make you guys my life difficult. Okay, so we have to mutually with each other. Okay, you make my life more difficult than I make it. I'm not trying to make your life difficult, but I want to make sure you guys learn something and it's fair to every student. Okay, so chapter 5. No, you actually, I tried this morning. You cannot access Canvas, but it's from Canvas. It's a lockdown browser. Once you do the exam, before that you can do that, but once you open your anything else before the exam, of course you can do that. If you finish your exam, you know that's a different story. Yeah. Okay. Yeah. Yeah.
Is there a reason we can't have just a physical printed test instead of using the computers? It's just
Yeah, I mean, this is a question of, I understand what you're saying. We have more than 100 students. And since multiple choice questions, it just, grading is avoided. And also mistakes is avoided during grading. So that isn't, yeah. Yeah. Okay, so chapter and chapter 6, yeah, the very, okay.
we still get 2 attempts.
Yeah, you still get 2 times. Yeah. Again, what I'm trying to do, give you guys a lot of confidence anyway. You can make mistakes, but at a second, and we drop one that you didn't do well. So the help you is not try to get you guys. Okay. Chapter MOSFETs, chapter BJTs. No, in addition to diodes, you guys already learned from chapter 4 to build any analog digital circuits, any like integrated circuits or very large integrated circuits, this as a building block. So if you look at any of the motherboard on your cell phone, for example, phone is that small. Sometimes what you call it, they call the CPU, and within the CPU, you probably got something around systems. What we meant is that you probably got a billion files. In this class, somebody, even though we like not join ESMO, join F, and somebody get the fundamental circuit. Actually break that 1 billion down. There's a single one that you have to understand, right? Of course, when you duplicate, until it becomes such a large system that can process information, can do all the job fast. So that's why it's very important. These devices are not that difficult to understand their principle. It's once you get learn these chapters, you're going to see. I'll make it in a way that you'll feel, wow, this is so simple. I mean, it's not that something. It's very difficult. Okay, this is a physical structure of a MOSFET. So when we build semiconductor devices from the very beginning, chapter 2 or 3, you guys learned that we need silicon. And you get silicon. Silicon is a sort of insulator. Silicon oxide or silicon dioxide insulate. It doesn't conduct electricity. But if we put impurity in it, it will start to have holes and free electrons. With the holes, we call it P. With electron, we call it N-type. With the hole, we call it P-type. P-type is an electron, we call. With those materials, we call this them semiconductor material. So they're not conductors, but not insulators. They're somewhere in between. So that's why they call it semiconductor. half conductor, a semiconductor. Also, how you put it. So the material are going to behave very differently. Take MOSFET. We're going to explain what MOSFET means. Well, a piece of silicon to make p-type like holes, positive ions. So when you put a p impurity, it becomes what we call a p-type substrate. So it's is on this substrate, we're going to make two electronic, we call well. Wells means like material. You dig a little bit out, so that area becomes hollow, right? I mean, it's not a hole, it's like a well. And it's a big thing. You probably can put water in it, it won't go anywhere because it's a well. Right? Put N material in it. So N is N plus, means it's rich of electrons. Not just N, but also it has more electronic. It's just on the semiconductor, it's on the high side. Okay, we put two of them. So each one is N, we put on both sides. So now imagine you have p-type material, then you have N. Between N and P, what do you have? It's a p-n junction. And that p-n junction is a diode. Right? So it's a junction, but of course we're not reference between the p-type and the n-type. And then in order to make this transistor, we have to connect wire so that it can conduct electricity. Now it's difficult to put a wire on. So metal down here, we call the body. So here we call p-type substrate, we call the body. This terminal, we often don't have to connect anything because really this piece of substrate just sits here, foundation. We're building stuff on it. Like when you guys play a game of Minecraft, yeah, you build stuff on top of it. So that foundation is like, it's like earth. We don't really do much of it. It's like ground. So often this is either grounded or floating. We don't do anything. But we do put a piece of material here on the n-type and here on the other n-type. So we put two pieces of metal, one on top of each n-type. Now look at this piece of metal. It's smaller than the well because otherwise you're going to get contact with this, right? We don't want that. So the piece of metal is smaller than the well's diameter, but it makes contact with the N. So if electrons flow outside, it will go to the metal. And then we can weld or soldering, we can weld a wire to the metal and it will conduct the electricity. Same thing on the other side. Then we're going to put another metal on top of the body, in the middle. But because we don't want to conduct the electricity, why no electricity, we can explain later. But we don't want to conduct electricity between the metal and the body. So what do? If you don't want to conduct electricity, you put insulator. So that's why we put a silicon dioxide. And then we put a wire on the top of the metal, but you just said you don't want electricity. Why would you put a metal? Well, you'll get there very soon. Everything is useful. Of course, somebody was very smart, invented this in the 1950s. That was bizarre. I mean, how could he imagine about it, right? But anyway, so nowadays we know that how they did it. So we're going to have a piece of wire connect here. Now, since we put a silicon oxide dioxide between metal and the body, so therefore there's no electricity actually flowing from this metal to the body. So now we have this thing built. So it's a 3D. You can see you got a piece of it. You got a piece of silicon. So the process, you got a piece of silicon. You put impurity of p-type material in the whole silicon, and then you dig a well, and you dig another well, and then you put a metal on here. You put a metal there. You put a silicon oxide, and you put a piece of metal here. Now MOSFET is built. Once it's built, it's going to work like magically. Okay. So let's see. So how, so how does this work? Well, let's duplicate it here. You got a piece of metal, and then you got here, and we got a piece of oxide. So what we're going to do initially, I'm going to apply a voltage between these two. Now remember, we have material is N plus, and this is P. So we're going to put some voltage. No, actually, sorry, this is wrong. Let me redraw this. I just made a mistake here. All right, I'll put a voltage between gate and the body. So why do that? One thing you already know that there's no electricity between gate and the body. So the top terminal we call it gate. No electricity, but you have like the top is a piece of metal and the bottom of the body is a semiconductor. So imagine what's going to happen if you put some voltage across this metal and another sort of metal. What happens in the middle from physics? You build a field. You have electrical field. Once you have electrical field, what happens to the electrons or the holes inside the electrical field? The electrons are going to move to the positive terminal, right? You have a field going from positive to negative. All the electrons are going to move. So what happens is that the electrons are going to move to this area. So electrons are going to move at this area. Because the electric field, the electrons are going to be attracted to the top to be close to the positive terminal of the voltage supply. You have a lot of electrons accumulated there. And what do you call that? So we call that a channel. I mean, if you look at the amplified circuit, you look, oh my God, there's a lot of electronics accumulated on the surface with a certain thickness. So look like a channel of electronics. So that is called a channel. Once you have that, a channel, what we're going to do is we're going to apply a voltage we're going to apply a voltage. Oh, what happened? It's still blue. Okay, that's fine. We're going to put a voltage between these two. So what we're doing now, we put a voltage between this side and the other side. So now we have a voltage. Connect to the metal and metal then to the entire material because they're semiconductor, they actually can conduct the current. Now in the middle, you have a layer of, or you have a channel of electrons. Think about what the electron is going to do now. They're going to flow. They're going to flow to the positive terminal, and then they jump over the voltage source. They go to the negative terminal, and they continue to flow. You had a loop. Once you have electrons continue to flow, what do you have? You have current. And the current, of course, in the opposite direction of the flow direction of the electronics. So now you have a current. So that current goes to this direction. And electronics flow this direction, and current flows this direction. So now you have current flowing. So apparently you can see here, the amount of current is related to, of course, the voltage. The higher the voltage, the faster the electron is going to flow. That's one. Secondly, also how many electrons do you have? You have more electronics, it's going to be more current, right? So between the channel, in the channel, how many electrons do you have inside the channel? The more electrons, the more current can flow. So the thicker the channel, the more electron it can contain, the more current you can flow. So that's how we build this device. Now, if you remove that voltage between gate and the body, the electric field is gone, and then you will not have any current because no electron accumulated in the channel, no current is going to flow. So that's why this thing is called metal oxide field effect transistor. So first of all, it's a transistor. Transistor means it's not diode. Diode has two terminals. Diode, right? Double. Transistor means trial. Three terminals. So it's a transistor. So it's a transistor. It got three terminals. It got this one here, we call it drain. And this one here, we call it source. In MOSFET, it's symmetrical. So basically, it's up to you to call which one drain, which one source. You can actually flip them. Current can flow in either direction. Problem, because if you look at the device, it's purely symmetrical. It doesn't matter. But in a conventional way, you have to define one so that we can make sure current flows from drain to source, from drain to source. So once you define it, let's do that. Of course, again, you can flip, you can do, but there are some other things too. So once it's made, when the drain is marked, actually we don't want it to bidirectional conductor current, but we flow current this way. And here we call it gate. We call gate because this determines whether you have current or not. You open the gate, or I guess you close the gate, you have current flow. You open it, current flow. And current flow is because we have electrons in the channel. Electrons accumulate here because electric field. So that's why it's called field effect. So the electron is because field electron. Field and on each one, we have metal. So we can model metal oxide. So metal oxide. So metal oxide field effect transistor. So in the middle, you have metal, you have oxide, and you have field effect, and then you have transistor, you have three terminals. So what's it called? MOSFET. All right, okay, we're here, MOSFET. Sometimes later on, people change that S to like semiconductor, but I would prefer it to, yeah, go ahead. It doesn't matter. But once we are connect the positive voltage on the side, that's drain. So on the right side is drain, left side is source. Yeah.
And the way that the electron.
Yes, always negative, right? So this is really a magical device. You read the in a book, also a little bit history about MOSFETs. So initially, people invented this device. They couldn't make it work. At that time, by junction transistor, we're going to talk next chapter. Then people didn't believe this would work, but they, making a lot of experiments, a lot of testing, a lot of fabrication. Eventually, they made it work. Today, most of our CPUs, electronics, a lot of stuff, I would say 95%, at least 90% are made of MOSFETs. The reasons later on we're going to explain, because these devices have very low on-state resistance. They have no current flow into the gate, which saves you power or energy, and they are very easy to control. You can MOSFET to call the real-to-real op-amps. Remember op-amps, when you guys did the problem, we have the situation where you have cut off because there's voltage drop on that transistor is 0.7 volts, but on here, you can go to 0.1, 0.2, or we build JFETs, it can go even negative. So which means it's going to conduct. with even a negative pole. So it's a beautiful device. It's versatile. So today's integrated circuits mostly are built up on MOSFET. We start because historically BJT was used earlier, later. Nowadays, the MOSFET and then BJT often or as much as MOSFETs. Okay, let's move on. Okay, so here gives you a big picture of the names of these devices. So on the right hand, we have the drain. In the middle, we have the gate, and the left hand, we have source. And the bottom is the body. As I explained earlier, body is typically not useful for us. And then in the middle, you have the channel region. But on here, I want to explain a few things. Did you guys see L? So that L is the length of the channel. So think about it. If the channel is very, very long, what happens to the current? Decreases because you have more resistance because it's long, right? So if the channel is wider, you can have more electrons, so you have larger current. So we have the width is in that direction. You can't see, but think about it. So this like this much thick, so we call that width. So the more W, the width, the more current, and the longer the L, the less current. So WOL is called length, width to length ratio determines how much current you can flow in a transistor. What else here we have to explain? I think that's it. So we're going to move on to look at examples, how current flow, or how much exactly current is going to flow in the device. Yeah. So now we introduce two terms. One is called VT. T is called threshold voltage. In regular MOSFETs, this is about 0.3 to 1 volt. If you build a JFET, like a vertical, some newer devices, this can go to negative. So, okay, so, but for now, think about the traditional MOSFET, 0.3 to 1 volt. This VT is different from the other VT we had in diodes. Remember that diodes we called VT, what do we use? It's the capital VT. So that VT is, what happened? Why? This is bothersome. Sorry about that. Something happened to this like smart device. Just doesn't. But that's not the writing. That little icon is gone. I called them many times, asked them to change this over to a newer system, but they never did it. It just doesn't, I don't understand. Screen share code notebook. Let's quit. Looking for that's my notebook. Smart. I am very sorry. Sure. Okay, maybe I just going to, I'm gonna write down here. Okay, so you guys know that VT, yeah, I can write down here. So this VT is called threshold voltage. The capital VT in diode we call thermal voltage. Yeah, go ahead. Oh yeah. So here you see here you have L is the length. So the longer the channel you have, the more resistance for electrons to flow. So it takes longer, right? Takes more time. You have less current. So current flowing is inversely proportional to the length. But if you look into the screen, there's a certain thickness. So the more thickness you have, the more electron you have, so more current can flow. So the total current will be inversely proportional to L and proportional to W. So what does it mean, threshold? So think about when you apply voltage between gate and say body, you have to have a certain voltage so that you can build enough electronics. If electronics, they accumulate, but that's not enough, you really like electronic jump here and there, you won't have current. So we have to have enough electrons to start to have current. So to have enough electrons, the voltage needed to do that is called a threshold voltage. So which means in devices, if your voltage is below like certain voltage, you wouldn't have current flow at all. Once you are above that voltage, you will have electronics enough to flow the current. But that's only one condition. But in order to have current to flow, we also need another thing called overdrive voltage. All right. So the overdrive voltage is the difference between gate source. So VGS is the voltage between gate and source. So in this case, source is grounded, right? So of course, body is also grounded. But in the future, we only talk about VGS, now VGB. So if VGS minus VT, so VT is the threshold voltage. So at this voltage, you'll have current. But how much current are you going to have? Depending on overdrive voltage. So if your VGS, if your voltage is exactly as VGS minus VT, your current actually will be like 0. But if it's a little bit more, and then you're going to have more current. So the difference between VGS and VT, we call it VOV. Your VDS from D to S, the voltage from D to S has to be larger than VOV in order to have a certain current. But in this case, we have gate voltage applied, but we don't have any voltage applied either drain or source. So in this case, would you have current? No current, because even though there's electrons, but the voltage difference between source and drain is the same, so therefore no current will flow. But once we connect voltage at the drain, you're going to start to see current flowing. Maybe I'll do this. Let me. This is important that you guys understand, at least for now, how the current is built and how the channel is formed. and why we call this MOSFET and so on. So this is going to be a really interesting concept. And in the next couple of slides, we're going to explain what we do with these two things. But let me open on my so hopefully I can do it from here.
Recording in progress.
So I'm going to quit this one. All right, I think I can write from here, hopefully. Okay, so now we have this MOSFET, and then we explain this one, then we explain the voltage. Okay, it's just slow on here. So now we have connected a voltage VDS. So now you guys see that they're all grounded. So the ground, typically the body is grounded. So all these terminals are connecting voltage to the ground, but of course source is grounded as well. So you have a voltage between gate and ground. So therefore it's going to form a channel like we said before. So you have a channel. Why? Yeah, you have a channel over here. Now we have voltage across the VDS, so you can have current flowing through here. Yeah, of course, to ground. That's how current flows from positive to negative electrons in the opposite direction. But this VDS has to be small, otherwise we're going to burn the device for sure. Later on, we know that just like a dial, we have to connect some resistance to limit the amount of current. This current is proportional to something. So that something is here, is this equation here. So remember what we last time we said there's a VOE, overdrive voltage, there's VT that we explained on the previous slide. So VT, you have the threshold voltage. So VGS has to be larger than, so VGS larger than VT to have current. And then we have VOE equal to VGS minus VT. That's called VOE. And then our current is related to, let's call this ID. So ID is related to two things. There's some constants. And then there's WOL. Remember we talked about WOL? The more W you have, more current. And here inside here, we have VGS minus VOE. And then the outside is VDS. So now you look at this expression, your current has something to do with VOV, or something to do with VDS. So that's the current applied between drain and source, and also something to L and W, and something to mu and COX. Mu and COX is the property of this silicon over here. So between gate and the body, you have this silicon oxide. That's the property of that. So this would typically is determined by like the type of silicon oxide, the thickness, and the area of that silicon oxide. That determines this. And W and L is how big is the MOSFET. Okay? It's how long and how wide. And then here VOV and VDS. So if we're given all the parameters, we will be able to calculate the current in the device. And depending on the values of VGS and VDS, we can plot them in a diagram. And right now, we talk to them about in linear region to that nonlinear region. But in the linear region, the current ID, again, I want to write this equation here. So ID equal to that's mu COX times W over L. Let's call it VOV, and then times VDS. This relation with VDS. So VDS, we put it on the horizontal x, and we put ID on the vertical x, and then we vary VGS. So if VGS is less than VT, no current. So that's this one here, no current. If VGS is larger than VT, you start to have current. But that current is proportional to VDS, which means if your VDS is 0, no current. But if your VDS more than 0, you're going to start to have current. The more VGS, the more current you have. So now this one is a very small region, okay? It's not like 5 volts, 10 volts. It's going to be like 0 point some volts, 0.2, 0.3 volts in this region. And we call this a linear region. And this current can be calculated using this expression. So right away, when you get off the class, you'll see some of the examples or exercises asking you to calculate the current by giving certain parameters. So this example, for example, this was given a certain parameters, like mu is given, TOX is given, and VT is given. They ask you to calculate the width of the transistor. So what we do is we start to calculate COX by using these parameters. These equations are given in the book. You can get this. Why is it called C? It's like the capacitance. So why is it capacitance? Because you remember this metal, and this is your oxide, and this is your body. So the COX is the capacitance between the gate metal and the body. So that's COX. Now, when you guys learn, how do you calculate C? So the length between the plates, right? You have two plates, the area of plate, and then the distance between the plate is L. And so that's how you calculate. So basically, this equation here is similar to that. Just doing the thickness of the silicon oxide, and then you're given this epsilon OX is the property, you get the capacitance. Okay, so once you get the here, like a mu and is given, so mu is the conductivity, the permittivity, and then using mu times C, you got K. This is the constant. It's a constant for given MOSFET. For different MOSFET, this number is different. But for this particular one, you get 388 microamp per volt meter, and you calculate VOV, the VGS minus VT. VT is given 0.1. VGS was given something somewhere. and 1, and VT is 0.5. So you got VOV 0.5. And then you calculate GDS is the conductance between gate and body. So you get this, because this was given at 1 kilo. RDS between its resistance between like here. So your RDS is equal to VDS over ID. So that's how you calculate the resistance for RDS given. So therefore we can calculate GDS, and then from GDS we calculate L and W. So LW is using the previous equation you had. The WOL, VT, VOV, and then so from here, you know the current, and you know all these parameters, VGS, VOV, and everything else you know. So you can calculate, your ID is given, you can either calculate WOL based on which one is given. So that's how we can get these numbers, and this example is in the book. So that only is true when your VDS is very small. If we increase our VDS to a larger volume, that equation is no longer right. So we go to the nonlinear region. In the nonlinear region, VDS is much larger. In this case, it's like we're going to connect a variable voltage source over at the gate. Over at the drain. We're going to vary, increase a little bit. And if you do that in a laboratory, you'll find, yeah, the current is going to increase. But not only just increase, but actually at some point, your current is going to be like this. So at some point, the current is like saturated. No more current. And then, in real life, that line will still increase a little bit, like you're probably going to see like this. But we can, most of the time we're going to say, yeah, that current is almost constant. Okay, we're going to later on to get into the point how to express that linear increase during the saturation region. So this is called that's the saturation region. Now, the little bit in the beginning we call it linear region. Actually, it got also a scientific name. It's called a triode region. So remember diode? So this one looks like a diode. It's a triode because it's terminal. They're called a triode. We can use them as a triode. So it's a triode region in the beginning. It's almost like linear, and then it gets to the saturation region, and the current doesn't increase anymore. Now we already have the current expression for the triode region, and now we want to have the current in the linear region. So in the saturation region, the current is only proportional, like WL and K. Like we're probably gonna use a Kn prime. Okay, so the Kn prime and W and L is given for any transistor. This transistor is made. During the design process, you can vary them to design different type of transistors or different size of transistor. But once manufactured, those numbers are not going to change. Then VOV, remember what VOV is? Is VGS minus VT. And VT is also given for any device. During the design stage, again, you can change VT by changing the property of the material. But once the device is fabricated, that VT is going to stay constant. It's not going to change, regardless who uses it, how you use it. So the only thing that will change the current is VDS, right? So because if I increase I'm sorry, not VDS, VGS. So if I increase VGS, my VOE is going to increase. If my VOE increase, my ID is going to increase. So imagine that. If I want to draw this curve on that diagram, how would you draw it? So in the saturation region, your current is almost constant, but it's proportional to VGS minus VT, and VT is constant. So if I increase VGS, what happens? My VOE is going to increase, my current is going to increase. So similarly, if I reduce it, I have something like this. So that's VGS 1, VGS 2 is larger than VGS 1, and VGS 3 is larger than VGS 2, and I have VGS 4 is larger than VGS 3. So I keep increase my VGS, my current is going to keep increase. But you already noticed it has nothing to do with VDS. So in the saturated region, my VDS can vary in a wide range. It won't impact how much current flows inside the MOSFET. That's a beautiful property of a MOSFET. And we use that property to design amplifiers. Now, we also use this property to design switch devices. We use it to design power electronics. We use them to design digital circuits. All of that happens here. So this slide basically I prepared ahead of time. Basically, further explains the what happens when in real life you have a channel, but because when current start to flow, current in the direction of so another direction is electrons. So electrons funnel. It's like everybody squeezes into like a cylinder, you know, and a lot of people on the outside, once you get the door, which is narrow, and your line becomes narrow and narrow, so it's like a funnel. But only have like one person going through the door at each given time. This happens to our electrons too. When all the electrons start to, they see the field and the field they want to move, you get more electronics on one side than another, because there's not enough like weight or enough room for them to squeeze in. This is called a channel effect. So a channel is no longer a flat, like even sized channel. It gets narrow on the D side, drain side, and it gets wider on the source side. So when you imagine that you have this tilted, like trapezoidal shape instead of so it's most likely it's going to be determined by how much electron can go in from the narrow side. But since there's more room in the middle for them to move quicker, like more room, so they can move quicker to the end. So ideally, the equivalent channel width is in the middle. So basically, what we're saying is that so we have a channel wide on this side, less on this side. We use average to represent how much current can flow, how many. So that's why if you notice how the market, like the alpha times VOE minus VDS, so that's how the channel start to change. And this is the current, this is current, and this current becomes ID over KWL, but instead of VOE, with VOE minus VDS, 1/2 VDS. Why? Because this side is VOV, but this side is VOV minus VDS. So therefore, the middle is VOV plus this side divided by 2. We got this. And including you got VOV minus 1/2 VDS. So when we plug in this number here, you can imagine that the actual current is smaller than the equation that we got from last side. And this is called effect. A channel effect basically reduces the total amount of current that can flow through the channel by a little bit. Not really by half, but it reduced by that much. Okay. So by this 1/2 VDS. So because this equation is not linear, so it's not reduced by half. Yeah.
So we use that equation in the saturation region?
Oh no, this is in the linear region. Yeah. This is still in the linear region due to channel effect. But in the saturation region, there's also a channel effect. But that's what we're going to talk about in a different way. So so in the cut region, you have ID that it can be expressed like what I explained in the previous slide. This is the equation that you have. So if I'm giving you W and L and Kn and VOV and VDS, you can easily calculate the current. Now this equation here, you can multiply by VDS to the inside, and you can vary by this one, and then eventually you get this. Now these three equations are the same thing, but just in a different way to express them. The reason we want to express them in a different way is we want to show how VDS is going to impact. So this is not obvious, but this one is more obvious because you get 1/2 VDS squared. Now, if VDS, the reason why I'm saying so, because if VDS is small enough, this term basically becomes negligible. And therefore, what you have is the previous equation. So again, the current is reduced by a channel effect. But that channel effect really depending on how much VDS you have. If VDS is not small enough, why I'm saying that? Let's say this is VDS 0.1. And the whole number here is also 0.1. You multiply these two, you got 0.01, which is about 10 milliamps, plus some number here. But if VDS 0.1, the square of 0.1 is 0.01, right? And divided by 2 is 0.005. So it's much smaller than this one, but it's not that small. But what happens if VGS minus VT is 1, but VDS 0.1? So the whole number here, you got 0.1, but this is 0.01. 0.1 minus 0.01 is 0.099, which is about 99% more than this number, which means it's negligible, right? So that's why this expression is more meaningful, because when VDS is small enough, we can neglect this one. This equation go back to our original expression. Channel effect becomes negligible. All right, so okay, so if VDS is larger than so we didn't explain when to use this expression, when to use that expression. Basically, is here, is VOV. Now remember when we say you know to be in have current. So but also the trial region be in the saturation region. You can be in either region. What determines that? That is how it's determined. If your VDS is larger than VOV, you're here. If your VDS is less than VOV, you are in the trial region. So once you got a transistor, you build a circuit. So initial step is you want to make sure your VGS is larger than VT, so the transistor can be turned on. It can conduct current. If less than VT, no current. Yeah. Here, and from here you have the two expressions. So ID and ID expression here and expression here. I probably don't have to remember, to save time. But if VGS is larger than, if VDS is larger than VOV, we move to this region. If VDS is less than VOV, we stay in the triad region. And the expressions for that is, yeah, so this is the one that for the triad region, and for the saturation region, you have this expression here. Either this one or this one, the same, because VOV is VGS minus VT. So that's your current for the saturation region. So when we have, yeah, go ahead.
So when do you use the first ID equation you showed us?
This, you mean this equation over here?
Like even before that.
Okay. No, I will summarize this one for you. Really, you have the two regions. So one region is, probably before I move on to this, a little bit further. You are ID is 0. That's my VDS is less than VOV. Right. So triad region to this K n times W OL, and then times VT OV D minus 1 of VDS squared. So that's in a equal to 1/2 K WOL times VOV squared. So this is the whole summary of the MOSFET. Look at VGS. If it's less than VT, no current. If it's more than VT, how much current will determine on VDS. If VDS larger than VOV, you got one equation. If VDS less than VOV, you got another equation. So by now you already know MOSFET has 3 operating modes: cutoff, triode, and saturation region. Now in real life, we build MOSFETs, and that MOSFET we saw before is called N-type or NPN. Well, if we look, just going back to the actual drawing here, it's easy to name them because you got NPN, so, or NPN. So P substrate, N wells, 2 N wells, so you get, and it's called N-type MOSFET. Now, we can also build P-type material. So in the P-type material, what you do is you exact opposite. You dope semiconductor with N-type material in the substrate. And on the N-type substrate, you dig some wells and you dope them to become P-type material. Now you have P and P. So you have P and P. So that's what we call a P-type material. A P-type BJT, so P-type MOSFET, or PMOS to be simple. Similarly, when you apply voltage, you get a channel, and when you apply current, voltage source, a current is going to flow between drain and source. So this is same as the N-type MOSFET or NMOS. Okay. Yeah, so the bottom figure shows the P channel instead of N channel because it's a P-type substrate. It's an N-type substrate. You have electrons. You have holes. Holes are going to accumulate on top. So basically, if you look at voltage, you apply a negative voltage instead of positive voltage, so that the negative voltage will attract positive holes to their surface to form that P channel instead of N channel. P means positive. I have N channel because those are. The thing is that people start to build two MOSFETs on the same substrate, becomes one NMOS, one PMOS. Because PMOS and NMOS are exact opposite in terms of flowing direction of current, so we call them a complementary MOSFET. So CMOS. So when you hear CMOS in the future, what is CMOS? CMOS is not a single transistor. It's a combination of a PMOS and NMOS on the same substrate. So the way to do that is you get a big piece body. On that P-type, you put an NMOS, like N-type in this area, and you put some thick silicon dioxide in the middle to make sure there's no current between this one. And then on that P-body, you dig a big well and then dope them with P-type material, N-type material. And on that N-type material, you put another small wells to put P-type material so that you form a PNP, and then here you have NPN. So it's like NPN, so it's NMOS, and then here you have PNP, so you have, this is a PMOS. And then this is a complementary MOS. The advantage of building this two MOS on the same is to save space. And it's going to be very, especially when we build digital circuits, it's very useful because something you want to close and open, you beat gate logic, you need a two MOS. So one conducting, not one off, not is now, but we use them in the triad region. We'll explain more later. So here, this example, it tells you like, they will let you know a process technology. Type of process is used to build the MOSFET. You guys probably hear the company, you hear about nanometer device, like people or like a building how that channel can be built. The smaller the channel, the more current you can conduct, right? So they want to build as small as possible, the L, but there's a limit. With the process, with all these like machines made by us, can only build so little, because they're building 3 nanometers. Build millimeters, okay, and micrometers, and then now nanometers, hundreds of nanometers. Now we're doing 3 nanometers. I just don't know how small they can go. But you probably guys hear also Moore's law, that we'll talk a little bit about that. That is really talk about the process technology, or the technology process that you can use. So Moore's law is not a scientific law. It's just by observation by this guy called Moore. He was looking at the electronics development, the manufacturing technology. He said every 18 months, the size of transistor reduced by half. Or in other words, you double the number of transistors on the same piece of wafer that you can build, on the same piece of silicon. How many devices you can build? It doubles every 18 months. And this law has been holding true since the 1980s until today. But people said after 2030, this law is no longer valid because today we already built 3 nanos. So the next 2 years, you're going to build what? 1.5 nano, right? And then the next one will be 0.75 nano. And going beyond nanometer is almost impossible. I mean, I don't know, but you guys know that. So the example says process technology, they're building this 0.18 micrometer. You can see, I mean, it is a technology, but it's still the old technology, 180 nanometers. And then you get all these parameters. You can find COX by the equation given in the book, and then they give you W/L ratio, so you can find W and so on, right? And then further you ask those questions, you can answer. Okay. So yeah, we finish section 1. You can start doing. So on Thursday we'll talk about section 2.